By now, you know how the market price is established and how the market price defines which generators run to meet the demand. The network makes sure that the generated electricity reaches the consumers. However, what happens when the network doesn't have sufficient capacity to accommodate for this? How do we deal with such problems when they arise? The learning objective for today is to understand what effect a lack of sufficient network capacity can have on the electricity prices. Usually, when we talk about a lack of sufficient network capacity, we are talking about a network connection between two bordering countries. These connections are usually high voltage transmission lines that are able to carry a lot of capacity. But especially when the market prices in the countries are different, there may be a huge demand for transport capacity. After all, everybody wants to buy electricity as cheap as possible. Today, we are going to use the example of two countries, France and Germany. France here is represented by a simplified merit order with units A1 to A6. The demand in France at this specific hour results in a market price that's rather low. In Germany, to the right here, the merit order is represented by units B1 to B6. In Germany, the demand at this hour sets the market price significantly higher. So in this situation and for this hour, the consumers in France pay less for electricity than the consumers in Germany due to the lower marginal cost for the generators. So, why should Germans stick to their own expensive generators? France is much cheaper after all. Because of this difference in price between the two countries, there will be an additional demand from consumers in Germany for the cheaper French electricity. This leads to an additional flow of electricity from France to Germany. Of course, this will impact the market prices in both countries. When German consumers shop in France, the demand in Germany will go down, and the demand in France will rise. The electricity flow between the two countries will thus cause the demand curves in each country to change. In France, the additional demand from consumers in Germany causes the demand curve shift to the right. This represents the increased demand for French electricity. And when the demand curve shifts, market clearing prices will lead to a higher market price. The original market price PA will change into market price PAB. In Germany, the reverse takes place. Since some consumers are purchasing electricity in France and no longer in their home country, total demand goes down. This causes the demand curve to move to the left, leading to a lower electricity price. The final electricity price in Germany will therefore decrease to PAB. Please note that when there is no lack of interconnection capacity between France and Germany, the market will lead to a situation where the market price in both Germany and France are the same. Both are then PAB. Effectively, both markets are now fully integrated. To demonstrate this, we can add the two curves together. The total demand curve represents the demand in France plus the demand in Germany. The supply curve has all the generator units in both France and Germany arranged according to their marginal cost. The market clears this integrated market at price PAB. This equilibrium price will be somewhere between the price we have in France and the one in Germany if the markets are not integrated. This equilibrium allows for efficient allocation of generation to the consumer. The cheapest generators in France and Germany are used for supplying the necessary electricity. This is therefore the least cost solution for both countries. Of course, you could counter that consumers in France are worse off. They pay more for electricity after integration with Germany. That's true. However, the generators in France benefit. They produce more electricity, partly also for German customers. When taking into account both consumption and production, the integrated market is more efficient than the two isolated markets separately. Now, suppose that to reach this market equilibrium, we need a transport of 10,000 megawatt from France to Germany. What would happen if the network is not able to accommodate this transport? When we say that the network has a limited capacity, this means that not all consumers in Germany are able to purchase the cheaper electricity available in France. Some transports are feasible up to the available interconnection capacity, but not all transports can be accommodated. The result is that the market prices in France and Germany remain different, although the price gap decreases a bit. The market demand curve moves to the right in France and moves to the left in Germany. But it can't move so far that the prices will end up in equilibrium. As you see, a price difference will continue to exist between the two countries. The transport network is congested. Congested means that there's need for more transport, but the network capacity is insufficient to provide it. Please note, we've chosen this situation between two countries, but it can also happen between two regions of a specific country, if the demand for transport capacity between the regions is higher than the transmission network allows. So, how are we going to deal with this remaining congestion? In the end, parties are benefiting the most when there's sufficient network capacity. However, for this sometimes huge investments are needed. In Europe, these investments often focus on cross-border capacity, since most of the network bottlenecks are on the borders. Investments in more network capacity make sure that consumers will be able to purchase electricity at the lowest cost. And that the market in Europe will perform optimally when all the transactions required by the market can be accommodated.